Now, just like with a double integral, we might sometimes need to do the integral in a different order and change the order in which we're taking this integral, changing the order of the variables. So suppose we have this integral where we're integrating x, y, z with respect to z first for these bounds, then x next from -1 to 1, and then y third from 0 to 4. And suppose instead we want to do this in a different order. Suppose we want to do x first, then y, then z. How would we do this? Well, the best way to go is to just look at this integral, look at the picture of what region it's describing, and then redo our bounds in this order, and then rewrite the integral in that way. So if we draw a picture of what region these bounds are describing, it'll look something like this. So z is from 1 to 2 minus x squared. So z starts at 1 right here. So this is 1. And then goes up to 2 minus x squared, which is a parabola, a downward-facing parabola. Then x goes from -1 to 1. So this point is -1, 1 in the xz plane. And then it goes to 1, 1. So x is going from -1 to 1. And then y is going from 0 to 4. So we start at y equals 0 in this plane, and then we go to y equals 4. So all of those bounds together describe this region, which is kind of like a half cylinder. Now, we could redescribe this region, except in this order now. So our rewritten integral is going to look very similar. It's going to be a triple integral of x, y, z, except our order is different now. Now we're going to do dx, dy, dz. So we just need to know what are the bounds on x, y, and z, and then we'll be done. So first, since we're doing x first, what are the bounds on x? Well, x goes from this left side, which is the left side of the parabola, to the right side of the parabola. Well, we need an equation for each of these sides of the parabola. Now, what is the equation of this parabola in general? The parabola that's graphed is z equals 2 minus x squared. And we want to describe x in terms of z to have our two bounds for x. So we need to solve for x in this. So if we solve for x, we get x squared is 2 minus z. So x is plus or minus the square root of 2 minus z. So that means that one of these sides is x equals negative square root of 2 minus z. The other side, this one is negative, and then this one is positive square root of 2 minus z. So this is square root of 2 minus z. And the x value over here is negative square root of 2 minus z. So that gives us our bounds for x. So x goes in between negative square root of 2 minus z all the way to positive square root of 2 minus z. So those are our bounds for x. Now how do we find our bounds for y? Well, no matter what x and z are, y always still goes from 0 to 4. Y can be anything between 0 and 4. So our bounds there are simple. But really, I'm getting ahead of myself. What is our strategy in general? After we find the bounds for the first one, we look at the projection onto the plane of yz. After we find the x bounds, we look at the projection onto the yz plane. If we project this half cylinder, or this almost half cylinder, onto the yz plane, that back plane, what do we get? We get a rectangle that looks something like this. And so for y and z, we just have to describe this pink rectangle in terms of y and z. So like I said, y goes from 0 to 4 in this rectangle. That's the bounds on y. So what can z be? Well, z in this rectangle goes from 1 up to 2. This z value is 1. This z value is 2. So the bounds on z are 1 and 2. Now we have the new bounds, and so this is a new way to write the same integral. So if we evaluate the integral in this order with these bounds, we'll get the same answer as before. So that's how we rewrite triple integrals in a similar way to how we would rewrite double integrals in a different order.